This is a pre-lab lecture for Lab 3 of ENP231, in which you will be studying an LED diode, a coin battery, and you will then be designing an LED fob, which really consists of both of these elements plus a current limiting resistor. So this lab actually takes place before we've talked about nonlinear devices within the lecture portion of the course. And this lab is designed in such a way to allow you to be able to do this lab without having that knowledge. So I'm going to show you in this pre-lab lecture everything you need to know for you to be able to carry out this design. Now it is assumed that you have already watched a video or learned about a load line. This was discussed in the source transformation lesson, which was part of the network reductions or network theorem lecture that was comprised of things like linearity, superposition, source transformation, Thevenin and Norton theorems, and then maximum power transfer. So you need to have watched the source transformation lesson, because in there I introduced the idea of the load line, and that's going to be important in this lab. The design work that you're going to do in this lab is going to be done graphically. Okay, graphically using a load line that will be representing the battery, as well as a curve then that represents the VI characteristics of the LED, and you will be able to do your design based on that. So first, what you're going to be doing in this lab is you're going to be getting to know both the LED and the coin battery that you're going to be using. So here I have drawn a representation of this particular LED. You might be using a different one in lab, but at this point for this year, where this video has been made, this LED that you'll be studying is a 5mm weight Piranha LED. So it's in a 4-pin package. There's actually only 2 pins to it that are electrically, 2 electrically unique pins, but mechanically it's got 4 pins, kind of like 4 legs on a table, so it sets up, it's more stable. And it puts out a nice white, bright light. And the symbol for a diode, okay, is this symbol that you see right here. And when it's an LED diode, so an LED light emitting diode, we put these little 1 or 2 little wavy arrows that represent photons that are actually being emitted from the diode. So that's how you know whether you have a regular diode or an LED diode. I've labeled the terminal characteristics for this diode as IF, which stands for forward current, and VF, forward voltage. So these are the current and voltage associated with that diode. Secondly, we have a coin battery. It's a CR2032 coin battery, the same type that might be found in your car fob, for unlocking your car. 20mm, I think, diameter. And you're going to be characterizing that battery as well. And that battery will behave very much like a Thevenin source. So I've labeled here the battery voltage VB and the battery current IB, and if we were actually to connect a load to that battery, which is what you will do in part of the lab, and take some measurements for various loading conditions, in other words, different battery currents, you would find that your data points fall on a straight line. Okay, if you were plotting battery voltage, measured battery voltage versus measured battery current. And it'll fall in a straight line, which would be a load line. Okay, so this is the battery load line. And it is modeled by VB is equal to some open circuit voltage minus some Thevenin resistance of the battery times IB. This, we've seen before, is really the terminal voltage of a Thevenin 1-port, comprised of a resistance R Thevenin and a voltage source VOC. And so we will actually represent our battery as this voltage source plus resistance. Okay, so there are 3 parts to the lab. One is you're going to characterize the LED. Secondly, you're going to characterize the battery. And then third, you're going to design an LED fob. Now in a subsequent lab, or maybe not officially in a lab period, most likely this will be made available in a subsequent Tuesday, where you can come in during your non-lab section, and we'll actually have a little circuit board that you can solder up that will actually produce this little LED fob, and you'll be able to take it with you, okay, and keep it. So you're actually going to design it. So the design is fairly trivial. You're only choosing 1 or 2 resistance values, but it still is practicing this idea of design. So when you there's going to be a lot more detail, specific detail in the lab, pre-lab document that you'll have to read, so I'm not going to go over all that now. I want to keep this video short, but essentially you are going to connect up a variable power supply, okay, to your LED through some current limiting resistor, and you are going to measure the voltage across the resistor, across the diode, and you're going to measure the current flowing through the diode. And you will take those measurements and fill in a table. Okay, so if you have like 2.0 volts, some current, 2.1 volts, some current, 2.3 volts, some current, and you are going to plot that, and you will find that it will have a response that looks like so, roughly. It will be nonlinear. You're not going to do any kind of modeling on this yet. We'll show you later in class. We'll go over a model. It's called a Shockley model, Shockley diode model. So you can actually predict this this VI characteristic, this nonlinear VI characteristic with actually an exponential equation. But we're not doing any of that in the lab. We're going to do just a graphical method. Okay. Secondly, you're going to have your battery, and you're going to do a similar thing where you will connect some load resistance to your battery, V battery, and you will measure, you'll close the switch here or short the wire, and you'll measure V battery and you'll measure I battery, and you'll again collect a couple data points, just a couple, enough to get a plot of V battery versus I battery, and you'll see that that falls on a straight line, and from that you're going to get your slope, and you'll have your open circuit voltage, and so you'll be able to produce a model for your battery, and that model will be nothing more than a Thevenin equivalent, an R, maybe I'll call it VB open circuit and RB for the battery. Okay, but those are just the Thevenin voltage and current. Now, the main portion of the lab then is once you have this data. So you'll have data points. So here you have just data points for the LED, and you'll have a model for the battery. Okay, so you have a battery model and you will have LED data. Those are the two first parts of the lab. It doesn't take a lot of data to get this, okay? Then you're going to use it to actually design your fob. So you will design LED fob. Now what does this mean? You'll be given a specification that says something like design I forward to be equal to, and I forget the numbers I actually asked for, maybe one of them is 6.8 milliamps, some small milliamp value. Okay, so what you need to do is you're going to take your battery and you will connect some resistance, call it R1. You're going to connect it to your LED. And when you close that circuit, you want to make sure that the current that's flowing through the battery, through the LED, is the designed or the specified current of 6.8 milliamps. Now, if this was a resistor, if this LED was some R, then it'd be very easy to design, right? You just simply say this current is going to be equal to VB divided by R1 plus R. So if you knew what R was, or say RL, if you knew what our load was, and you knew what the battery voltage was, all you need to do was to find R1. Now, actually, let me correct that slightly, because this guy, based on your data that you've measured, you would know that this actually is a resistance plus a battery voltage V. We said V battery open circuit, and this is R battery. Okay, so what we really have, oops, let me redraw this. We have V battery open circuit. We have RB. We'd have some external R1. And then if we had a resistor, which we don't, so I'll come back and address how we deal with the diode in a minute. But first let's understand what we'd do if we actually were trying to design this circuit to have a current of 6.8 milliamps for a given R load. Okay, we would then say this I forward, if that's what we call it, would be VB open circuit divided by the sum of all the resistors. Now, we would have been given the value of the battery. Well, actually, we weren't given it, but you determined it. You measured it in the part 2 of the lab, right? We also would know RB, the battery resistance. That comes from that part 2 of your lab as well. We would be given our load. This would be provided. Assume that would be provided. So therefore, we just have one unknown, okay, to find. This is what we mean by design. By designing the LED fob. Okay, it's not a big task. Just find the value of R1. If the load, which is our LED, if that was just a resistance RL, this would be very easy to do. We just solved it right now. The caveat, or the challenge, comes in when our load is not a resistor. It's a nonlinear diode, right? So how do we do that? We're going to solve that graphically. So before I go back to showing you the scenario with the diode, let's solve this same circuit, the one here where we have a load resistance. Let's solve that graphically. So here's how we do it. I'm going to first draw the load line of my battery. I'm going to plot the V of the battery versus the I of the battery. And I know that that's going to be a straight line. So this is VB, okay, and this is as a function of IB. This is going to have a slope of minus RB, okay, and then we will plot the VI relationship for our load. Okay, so we have VL is equal to RL times IL, which is IB. Okay, same current. So that's a straight line also, but it's it intersects 0, and it's got a positive slope of RL. Okay. Now the question that I have is, what is the significance of this point right here where those two lines intersect? At that point of intersection, there is a common current flowing through the battery and through the load, and that current we'll call I'll just call it capital I. I'll call it IQ. Okay. What this intersection signifies is that at that point of intersection, the two circuits, that is, in green, we have the battery voltage source, open circuit voltage, and the battery resistance. This voltage VB is going to be equal to the voltage that would be generated across a resistor RL. Okay, when, this is VL, when a current IB flows through it. So they share the same current and they share the same voltage. Well, how would that happen? Physically, we have these two networks, if you will. That intersection point corresponds to when these two circuits are actually connected together. Okay, so this intersection here corresponds to the solution. This intersection is the solution to this circuit right here. Let me show it to you another way. If we started out with this circuit here, we had RB, R1, and VB open circuit. Okay, call this I. If you went to solve this for this current, we would do just simply I is equal to, since it's a single loop, I can just say VB open circuit divided by R1 plus RB. I realize, RL. I realize I've left R1 out over here. I've done that on purpose. I'll bring that back in here in a moment. If I rearrange this, okay, so what I've done is I've written this expression for I straight from this single loop circuit, ignoring this plot over here for a moment. I'll come back to it. If we rearrange this current, I can write I times RB is equal to VB open circuit minus I times RL. Oops, wrote that wrong. I times RL is equal to VB open circuit times I minus I times RB. Okay. Well, this right here is our purple line. Okay. Oops. Over here on the graph on the left. And this here is the green line. Okay, that has the slope of minus RB. So what we're saying is that at the solution point, at the operating point of this circuit, the left side here is equal to the right side, which is the same thing as saying that these two curves, curve 1 and curve 2, are equal. So another way to actually find the current flowing in this single loop circuit right here would be to use a graphical method like I've done here. Draw a load line of the battery. In other words, it's open circuit voltage and its Thevenin resistance RB, and then draw a load line or not a load line, draw a V versus I curve, this purple curve, for the resistor. And at the point of intersection, that is your solution. Now in the case of a resistive load, this is not necessary because we can quickly and straightforwardly solve for the current. We don't need a graphical method, though it might be insightful to use it. So it's not necessary. However, when we use have a nonlinear element, we're going to use this precise method because with a nonlinear element, you can't solve the equations in a closed form. Now before we do that, lastly, let's look at this one last time and ask the question, if you were asked to set the operating current to 6.8 milliamps, how would you do it? What things could you change? If we look at our current over here, and we're trying to get this guy to be 6.8 milliamps, then in general we have three things we could change: the open circuit voltage, the load resistance, or the battery resistance. Unfortunately, all three of those are fixed. We don't get to choose those. Now you might say, well, I can choose the load. No, imagine though, in this case, you're given some load for which the resistance has been specified, because that's in fact what's going to happen with the LED diode. You're going to be given this LED, and you don't get to pick what that LED characteristic is. You're just given it. You're going to measure it, but then you've got to work with that. So if we can't change any of these three parameters, we can't actually control the current. In order to control the current, we need to add another external resistance. So although we can't change RB right here, we could change a resistance that we placed in series with RB. In other words, this R1. Now that would not ever result in making I any larger than it would be without an R1, but it certainly can make it smaller. And it turns out in the design we're doing that the current we're asking you to design this circuit at is a current level that is lower than what you would actually observe if you were to just connect that battery directly up to the LED. Okay, so let me go back one last time and modify this load line and these equations if I add in R1. So if we add in R1, then over here we're going to have plus R1 here, and we'll have plus R1 here. Okay, and our curve is no longer going to be this original green line. It's going to be a steeper green line. It has to be steeper because the slope is minus RB plus R1, and we don't have any negative resistors. So do you see now that if I choose increasing R1s, I can move my operating point down. So this would be for increasing R1. The larger I make R1, the steeper that load line for the battery. Now it's the load line for the battery plus, let me augment that, it's going to be, it's going to be the battery open circuit voltage plus RB plus R1. Okay, so that's our Thevenin, our equivalent source for it's really the Thevenin equivalent for our battery plus this external R1 resistor. And now we have something that we can turn, right? Whenever you're asked to design something, you have to have some variable that you can adjust in order to meet the requirements. The variable you can adjust in this case is the value of R1, this one external physical resistor that you're going to place between the battery and ultimately this LED. Okay, so now we can return to the LED, and I can show you in closing here the method for doing the graphical design of the LED fob for the case where the load is a diode. we still have our load line for the battery plus this external R1. This, just to be clear, this is the design parameter. Now, instead of having a nice straight line like for an RL, what we're going to have is we have this nonlinear curve for the LED. Remember I showed you, I just drew this up here initially. That's the type of VI characteristic you're going to see for your LED. So maybe it'll be something that'll look like this. Okay? And the operating point is going to be found right here. Now this will be I forward, or IL. This will be, actually that's, sorry, V forward. This will be I forward. So if we're trying to design this current, or the LED fob, to operate at 6.8 milliamps, then what you get to do is you get to adjust R1, okay, such that the operating point is going to be exactly at 6.8 milliamps. So let's see, this current here is too low, and that would correspond to a resistance R1 that would be too large. Right? Remember, the larger the R1, the steeper the slope, because the slope is minus RB plus R1. And here the current is too high. And so we've chosen here an R1 that is too small. So what you will do is actually graphically, you can do this on your lab book. If you have plotted data as you measured the LED diode current and voltage, and if you plot that on a scaled plot in your lab notebook, you can then draw this load line, and literally what you will do is you will know the open circuit battery voltage, V open circuit, or VB open circuit, that you're going to measure. That's easy to measure, right? You just measure the voltage coming out of the battery when there's no current. And then you will pick what current you want to operate at. And you will have 2 points. There will be 2 points. The first point is this point here, right? It has to intersect, at zero current, it has to intersect the open circuit battery voltage. And the second point is the operating point. So these are the 2 points that you will fit a line to, a load line to. So fit the battery, fit the battery plus R1 load line to pass through the 2 points. They will be VB open circuit, comma 0 amps, right? And the second one will be, this will be TBD. We don't know what that's going to be, TBD, and 6.8 milliamps. When I say TBD, this is going to be determined by the LED curve. You draw that line through those 2 points. Then you determine the slope. Then you extract R1 from the slope, and then you build your circuit, which is going to be just the battery, the battery, an external resistor R1, and then your LED fob. I'm sorry, your LED. Now, in the actual lab handout, you will see an electronic version. You will see actually that there is one other little thing to this LED fob. All right, I'll let you read about it in more detail, but essentially this is what we want to do. We would like to have, you're going to be given your battery. And actually, I should have told you the whole time you're doing this, I mentioned just one battery here, but we're going to have you actually design this using 2 batteries in series, okay? And you will treat that as just like one single battery. We actually have a battery holder that fits 2 batteries in it and has just 2 leads coming out of it, and you'll treat that as if that is the battery we're talking about, though physically there's actually 2 batteries in there, okay? So you will be given these 2 batteries, treat it as a single battery, your LED. You are going to be given 2 resistors, or you're going to be told to find 2 resistors. And then you're going to be given 2 little switches. And so we've added another little design challenge in the lab. The first design challenge is just what we've been through. Determine the resistance R1 such that when the LED is powered from the battery, or these 2 batteries in series, the current is 6.8 milliamps, or whatever the lab asks you to do. But what we really want is we want an LED fob that actually could give you a bright and a dim output. Okay, and the idea is that if you press let's see, let me remember what I said. If you press one of the switches, it will turn on dim, and I forget, I think the current setting there is a 0.5 milliamp, something like that. And if you press both switches, the LED will put out the 6.8 milliamps. Now don't quote me on this, look at the instructions. I may have asked for something a little different than that, but that's the basic idea. And I tell you exactly how many parts you need to do this. You need just your batteries, your LED, 2 resistors, and 2 push switches, push button switches. And so with those 6 elements, you are tasked with, quote unquote, designing a schematic. Figure out, how do I wire up these 2 switches and these 2 resistors so that it functionally acts as described. It turns on dim when you press one of the switches. If you press the other one, I don't think anything is supposed to come on, and if you press both of them, it'll come on bright. Okay, and the idea behind that is if you're going into a dark room, your roommate's sleeping, and you need to look for something, and you don't want to wake them up, if you pressing one button made it dim but pressing the other button made it bright, then you're at risk of pressing the wrong button and accidentally turning on bright when you really want dim. So what we really want is we want to make sure that the only way you're going to get a bright output is if you press both the switches. If you happen to press the wrong single switch, then the LED just won't turn on, but then you would just know to press the other one, which would turn it on dimly. So what that means is that because you are going to be given these 2 current values, 6.8 milliamps and a 0.5 milliamp, you're going to have to repeat what we just went through, choosing R1. You're going to have to do it a second time to find a resistance that will give you that dim operating current, 0.5 milliamps. And then you will have those 2 resistor values, and at that point you'll be able to draw this circuit, or think about, how do I draw this circuit such that I get this functionality that's being requested. So that's the lab, and I think this pre-lab has given you enough information to be able to at least know the theory, the theory that's needed to go about this design. What you need to do now is go and look through the lab handout to look at the procedure that will lead you through some of this. You will be given more specific instructions on how to set up the measurements for being able to characterize the LED diode and the battery. Okay, but you won't be told, obviously, what this circuit is. How do you wire these up? That's kind of a little creative piece for you to carry out. Now, there is one other video that I have for you to watch, which is going to give you a little tour of the lab handout. We're using a new format that we're going to try to standardize on for the rest of the semester, and so it gives you a little tour of what those different standard sections are and some further instruction that's specific to this lab. So you want to make sure you watch that as well.